Well, good morning again, or good afternoon, as the case may be. As you know, we got interrupted this morning, and I had to leave a little bit early. And so, as this afternoon, I'm going to try to work through a few problems from section 5.8, just to be able to give you, if you really need this extra time with me, it will maybe give you a head start on doing homework questions. So we're going to continue with the integration, and I'll just simply uh, change over to the other screen and start working problems. It's going to be very difficult. I don't ever work problems without having students in front of me, and it's very difficult to work problems without having you to correct my mistakes. So uh, you can still do that when you're watching this video, correct my mistakes and work the problems correctly if I do it incorrectly. So just to review, since this is maybe a standalone video to some extent, recall that we have the integration formulas, the integral of du over the square root of a square minus u square. That's the format, and this gives us arc sine of u divided by a plus c. We want to use the formula, the integral of du over a square plus u square, and this gives us an arctangent of u over a. With this formula, the derivation, we see that we also need a 1 over a out in front. And likewise, when we do the integral of du divided by the absolute value of u times the square root of u square minus a square, you see how the difference, a square minus u square versus the variable coming first before the minus sign. This likewise gets a 1 over a. This is the arc secant of u over a. Notice all three of these have the u over a, in this case, plus c. So those are the three formulas that we're trying to practice with. And so we just started working examples. And it's all about u substitution. And so the first few problems, just to illustrate some of the properties that we do use, if we have 12 divided by 1 plus 9x squared. Some of the observations we make in terms of using this. First of all, the 12 can come right out in front of the problem, and we have dx over 1 plus 9x squared. So this is a problem in which the observation is made is that a squared is 1, therefore a is 1. The u square is 9x squared, which makes the u 3x, and the du is a derivative of that, 3 dx. You see, it's very necessary to make sure you understand that we have to have du in the top. Now, clearly, this is a problem that's using the arctangent problem, but you see that 1 over a, arcsecant u over a, you need to have what u is, a, all of these parts need to fit in there. And you see, so far, though, this formula doesn't work because we don't have the du on top. Du is 3 dx. We need to have 3 dx up here. And so what we do to have the 3 dx is we come up here and we put a 3 in there, and we put a 1/3 out front. because 1/3 of 3 is 1. So it has it's an algebraic property. Nothing has been changed. Well, what is changed is the fact that we now have the integration part. The formula is of the form du over a squared plus u squared. And so that still goes. So now we can do the multiplication here. 1/3 times 12 is 4. And now to the integral, we apply this formula. We need 1 over a. Well, what is a? A is 1, so that's 1 over 1. Arctan u is the 3x over a, which is 1, plus c. So without all the extra parts, and now you just write 4 arctan 3x plus c. And that's the way you finish that problem. So not a hard problem, not hard to see which formula to use. And it's just a matter of how do you make it fit. And the big issue is to make sure that you know what u is so that you can account for du. That's the all important part, to get the du in the formula. So we'll keep those formulas handy. And now we'll go out and work some more problems. Now, here's a problem that shouldn't be too much of a problem. 1 over x square root of x to the 4th minus 4 dx. That's the way it comes to us. Now, it sort of looks like this is a good chance to use this arcsecant because of that x on the outside. And so this is what we're going to keep in mind. We're just going to write this over here. This is, you see, you got to always have these things in mind. That's why you memorize formulas, because they'll be in your mind. And you got to have that in your mind somewhere to make it fit, even without knowing the answer over there. That's not the part. We got to make the formula fit that form so we can use that formula. So we're just going to simply assume that x is greater than 0, and then we'll be happy that we have absolute value x there. Okay? Then, because obviously x is either going to be greater than 0 or completely less than 0. It could never be 0 because this would be an undefined problem. So assuming x is greater than 0, we now look at this thing and we look at the different parts. We can see that a squared is 4, and therefore a is 2. And we see that u squared is equal to x to the 4th. You see, so everything is determined by this u squared minus a squared. That's doing everything for it. U squared is x to the 4th, which makes u x squared, which makes du 2x dx. Now, you see, there's something going wrong here. We got to have absolute value of u out front, but u is x squared. And all we have is an x. How are we going to get an x squared there? But what comes to the rescue is we need an x in the numerator also. And so what we're going to do with this thing is to make it fit. We're going to make it look like integral. And we know we need an x squared down here, and we can have that if we put an x in the numerator. And now we have the square root of x to the 4th minus 4, you see? And now we at least have accomplished the fact that we have u right out here, and then we have the square root of u squared minus 2 squared. You see, that's what we're seeing. And do we have du up here on the top? Well, no. But we have at least achieved having an x up there. And then we can, of course, bring the dx from out here to the top of the fraction. So what's missing up there is a 2. When I'm missing something, I sometimes like to insert it with a parenthesis like that, so you can sort of see that it's an insert. And I take care of that by inserting a 1/2 out in front. Now the problem fits perfectly because we have 1/2 out in front. But then this is, in fact, du over u square root u squared minus 2 squared. So we can fit the formula. Now we need to know what the formula looks like. So the formula looks like 1 over a arc secant u over a plus c. So I need 1 over a. That means 1 over 2. 1 over a arc secant u. What was u? U is the x squared over the a, which is a 2, plus c. Of course, you'd probably want to rewrite your answer as 1/4 arc secant x squared over 2 plus c. And that one might be a good way to write the answer to this problem. So we learned a little bit more there when we have higher powers, how to get that extra x in there when we needed it. We'll just change the page and come up with another problem here. Here's another one that looks similar to that. It's the integral of 5 divided by x, the square root of 9x squared minus 11 dx. Now, again, this looks to me like a du over absolute u square root of u squared minus a squared form we want to try to match this up to. In this case, it's sort of weird because our a squared is equal to 11, making a equal the square root of 11. So that's sort of ugly, I guess. We do see that in this case, we have that u squared is 9x squared, which makes u 3x, which makes du 3 dx. So there's a couple of things that we've got to fix about this thing. First of all, we see that that 5 has no place in the problem, so we get that out in front. And now we have our dx up here, and we have our x and our square root of 9x squared minus 11. So we need to make this thing fit the formula. And so what we need down here, since our u is 3x, and we need an absolute value of u out front, we need a 3 on that. Now, you see, what we were going to do is we're going to get the 3 here, but if we put a 3 out here, that's in the denominator. And you see, that means that we need to put a 3 over 1 out in front of this, because that's like putting a 3 in the numerator here, but we don't want that 3 in the numerator, do we? Or do we? We put the 3 here, we can do it out there, so now we have u and all of that. But then we say, do we need a 3 in the numerator? Oh, I don't want to put that 3 out there. I'm just going to put him back in here. So rather than putting him in there, put him in here. That's where he belongs better. If I've confused you, I'll write it that way. This is 3dx over 3x square root 9x squared minus 11. So just like we used on that previous problem, we had to get an x up here and we put an extra x down here. So we've got this time we needed a 3 in both places, and so we put a 3 both in the numerator and denominator. That gave us our u on the outside of the radical and our du up here. And so the 5 we got out there. And so now again we use the formula, arc 1 over a arc secant u over a. So what we got to do to this thing, we keep the 5 there. We need 1 over a. What's a? A is the square root of 11. So this is going to be 1 over the square root of 11 arc secant u is 3x over a square root of 11 plus c. And it's not typical in an environment like this to worry about rationalizing that, so you might leave that as 5 over square root of 11 arc secant 3x over square root of 11 plus c. You might, if you wanted to make that 5 square root of 11 over 11 arc secant 3x, but it just almost would never occur to anybody to get that radical out of the bottom right there. Just leave it like it is. Doing all of this just makes it messier rather than making it prettier. So there you go. Do whatever WebAssign makes you do, and that's about all you do. All righty. Let's see what else is going to come up here. Here's one that's sort of weird. Integral of the sine of x over 7 plus cosine square x dx. So thinking back over your formulas here, you sort of realize that this looks like an arctan problem, if it is going to have any chance at all, because we got the sum of squares in the denominator up here. And we realize what's going on now, because you see here, we see that a square is 7. So a, like in that last problem, is a square root. A is the square root of 7. We see that u square is cosine square x, making u the cosine of x, and then du, the root of cosine x, is negative sine of x dx. So we almost have a du up there, not quite. We're going to take this and rewrite it as negative sine x dx over 7 plus cosine square x. And so now it fits the formula exactly, the integral of du over a square plus u square. And that is 1 over a arctan u over a plus c. So what do we get out of this? Well, the negative is going to stay with us. And then it becomes 1 over square root of 7 arctan u is cosine x, divided by a, again, that's the square root of 7, plus c. And so we made this fit the formula. All of this part here, you see, was required all of that to be your du. And a squared plus u squared. And so formula fits, you get it done. Not bad. Not bad at all. And here's one that's just as quirky as can be. It's really sort of a omen of things to come, really. Uh, it's the integral x minus 3 over x squared plus 1 dx. Now, the x squared plus 1 reminds us very much of the same arctangents, a squared plus u squared. And that can be written either way, a squared plus u squared or u squared plus a squared. Either way, this is fine. But what's funny is this x minus 3 up here. How are we going to deal with that? And what's good about this particular problem is that x minus 3 just messes everything up. It's not going to be a du. And the trick is, just like in fractions, common denominators, you can combine the numerators. Well, when you have a combined numerator like this, you can split it apart into two fractions. And so this can be thought of as the integral. You see, this is the same thing as x over x squared plus 1 dx minus the integral of 3 over x squared plus 1 dx. So this is going to be a problem that really is going to come up again in chapter 8, where we'll talk about techniques. And that is when you got a numerator that can be split apart into the sum or difference of two things, you can split the whole integral apart. And you see, algebraically, this is totally equivalent. Now, this gives us two different integrals that look very similar. One has an x in the numerator over x squared plus 1. The other's a constant. And here's what we're going to have to do. We're going to have to look at this differently. In this case, we're going to let our u be the whole denominator, because then du is 2x dx. And you see, we can make this fit the form of the integral of du over u, which is ln absolute value of u. That's what we're shooting for in this problem, and we can have it simply by inserting a 2 there and a 1/2 there. And now you see this is 1/2, and then this whole thing is du over u. So this is ln, and we don't need an absolute value on this x squared plus 1. And we're not going to put the plus c yet because we're just plus c for the whole problem. So this part of the integral is 1/2 in the natural logarithm. But this one, we need to get the 3 out of there. And then it's just going to be dx over x squared plus 1. And you see, that's an a is the 1, and dx, that's just 1 over 1 arctan x over 1 plus c, just straight out of the package, an arctan integral. And so we're finished. 1/2 ln x squared plus 1 minus 3 arctan x plus c. But an interesting problem, because it's got an interesting technique of how you can sometimes split that numerator up. If you have a definite integral, there's no big deal in terms of what's going on. You still integrate it exactly the same way. The integral from 0 to the square root of 2 of 1 over the square root of 4 minus x squared dx. You see, coming back to that, it's pretty easy to see that this is going to be one of our arc sine type problems. We can remember that formula. In other words, we're remembering the integral of du over the square root of a squared minus u squared is arc sine u over a. That's what you're remembering. And so what I'm looking at this is a squared is 4, so a is 2. And u squared is x squared. U is x. Du is just the dx. So this is already pretty well fit in the form. And so this is just going to be arc sine of u being x in this case, over a, which is 2. But instead of saying plus c, this time we draw a vertical line and we put our limits on that vertical line, 0 and the square root of 2. So we've done our antiderivative, but now we need to plug this in. So this is arc sine of the square root of 2 over 2 minus the arc sine of 0 over 2. So this time we get to do things that from the last section. We have to actually evaluate the arc sine of the square root of 2 over 2. And you see, that's where we have to remember that the sine of pi over 4 equals square root of 2 over 2. That knowledge is what enables us to say that the arc sine of the square root of 2 over 2 is pi over 4. And then we know that the sine of 0 is 0. So the arc sine of 0, and remember that 0 over 2 is a 0. So the arc sine of 0 is 0. And so our final answer here is just pi over 4. So definite intervals have numerical answers, and they do have, with the case of these arc sines, we've got to use some of these values that we had from before in order to fill in there. Here's another problem that involves something we need to get used to looking at. Here it is. It's the integral from one to 7. Integral from 1 to 7 of 1 over 9 plus, and look at this, x plus 2 squared dx. Now, excuse me, I'm about to sneeze. I'm thinking here that this has got to be a du over an a square plus a u square integral. You know, our old friend, 1 over a arctan u over a plus c. I should always write these over here a lot of times just so I can know what I'm looking for, knowing how I'm trying to fit. And I got to make sure before I do it, I got to fit this. So you see my a square is 9, making a 3. Here's what's a little bit new for us on this one. U square is in the x plus 2. It's the quantity being squared. U is the x plus 2. And du is just dx in this case. So you see, this is already in the perfect form of du. It's just 1 dx. And then it's a square plus u square. So we fit the formula perfectly. And so this comes down here immediately as 1 over a, 1/3, arctan u, which is x plus 2 over a, which is 3. And then that whole thing is evaluated from 1 to 7. Now, when you evaluate this, I would factor out the 1/3, and then I would write arctan of 7 plus 2 over 3 minus arctan 1 plus 2 over 3. So we substitute the top number in first, and then the bottom number in second, subtracting in between. So this is 1/3. This is arctan. This is 9 over 3 is 3. And 3 over 3 is 1. So again, we have two arc-trig functions we have to evaluate to see if we can do anything with them. Now, the tangent is of pi over 3 is the square root of 3, but it's not a 3. And so arctangent of 3 is not one of those things that we have an exact value. So this is just going to be left in exact form, arctan 3 minus arctan 1. However, we don't have to leave it that way. We can actually know a value for arctan of 1, which is pi over 4. So you might leave your answer looking something like that. Or you can make it 1/3 arctan 3 minus pi over 12 if you wanted to. Either way. Would be another way to write your answer. So either way, looks pretty, whatever works. That's the way it goes. There's this look down here of x plus 2 squared is going to come up in the next few problems, where we're going to use what's called completing the square. Let me just do a little review on completing the square. Remember that if you were doing this when you were solving quadratic equations, x squared plus 6x plus some other number plus 1 equals 0. If you had to solve that, that would not work with factoring. You couldn't factor that. And you could use a quadratic formula, but another technique for doing this is completing the square, where you write this as x squared plus 6x equals -1. And then you want to complete the square on this to make it a perfect square trinomial, meaning it's going to be x something squared. Because that's plus, you make it plus. You take half of the 6, and that is 3. I'm going to change this x squared plus 6x by adding something on here. You're going to make it the square x plus 3 quantity squared. And you do that by taking 3 squared is 9. And you add 9 in there, and you add 9 to both sides of the fraction. So then, to the equation. So then this becomes x, this side is x plus 3 quantity squared, and this side becomes an 8. Then you finish the equation out by taking the square root of both sides, which is plus or minus 2 square root of 2, or finally, x equals minus 3 plus or minus 2 square root 2. That's the completing the square that you've seen before. But right here, this is the part we want to capture from this. Suppose we had an integral of 1 over something that had some of this part in it. 1 over 5 minus 6x minus x squared dx. And the question is, how can we deal with that? And the answer comes to looking at this whole denominator and seeing if we can complete the square on it. And so this is the denominator I have. And I want to work, I don't have an equation, so I'm going to have to work entirely within that. And so here's the first thing I want to do. All those minus signs confuse me. So I'm going to factor out a minus sign and rearrange this. And I'm going to write this as x squared plus 6x. And I'm going to put minus 5 way over here to the side somewhere. And what I want to do is I want to complete the square on this thing inside so that this first part will look like x plus 3 quantity squared. Why x plus 3? Just like before, half of 6 is 3. And I can have it that way if I add 9 up here. But since I don't have two sides to an equation, what I do is I add 9 and subtract 9. Now, these three terms are taken care of as x plus 3 squared. These two combine to make it minus 14. Now, multiplying through by the minus sign and rearranging it, this becomes 14 minus x minus 3 squared. Now, there's the algebra that enables me to rewrite this problem as 1 over 14 minus x minus 3 squared. And I'll just go ahead and put the dx up here. Now, I'll look to see if this meets our arctangent format. A squared is 14, so a is the square root of 14. Not bothered by that. U squared is x minus 3 quantity squared, making u x minus 3 and du dx. So see, it does fit the format just perfectly. So this is 1 over a, 1 over root 14, arctan u, and u is this binomial, x minus 3 over a square root of 14 plus c. And so this problem, by the method of completing the square, enabled us to use that arctan formula. And that completing the square is the way we're going to handle a lot of these problems that have squares that are not quite of the form we wanted to look at them with. And so again, you just have to get used to that. So we'll get used to it on another problem. Here's the integral from 0 to 2 of dx divided by x squared minus 2x plus 2. So the problem is that's not quite an arctangent, you see. It's not a square minus a number minus a square. And so we got to see if we can figure out what to do with that thing. And what we want to do, first of all, is we want to take this x squared minus 2x plus 2 and convert it into some squares. Can we do that? Well, of course we can. This is going to be x minus, and half of 2 is 1 squared. How can we do that? Well, we have to add 1 and subtract 1 here. And so these three become x minus 1 squared, and then these two become plus 1. And so what does this now look like? It looks like dx over 1 plus x minus 1 squared. And so you see, a squared is 1, a is 1, u is x minus 1, well, u squared is x minus 1 squared, u is x minus 1, du is dx, so it fits the form perfectly. So this is equal to 1 over a arctan u over a, which is x minus 1 over 1, and then this time evaluated from 0 to 2. So I'm going to rewrite that a little bit. Arctan of x minus 1 evaluated from 0 to 2. So you substitute a 2 in there and you get arctan of 2 minus 1 minus arctan of 0 minus 1. Arctan of 1 minus arctan of negative 1. Now, arctan of 1, we know the tangent of pi over 4 is 1, so that's that. Minus, and the arctangent of negative 1, remember the tangent uses the minus pi over 2 to pi over 2, so this is the negative pi over 4 here. So that's pi over 4 plus pi over 4 gives us pi over 2 for our answer. Now, one thing I want to remind you that anytime you're doing these definite integrals, you could actually do these on your definite integral you can do on your calculator. See if I can get this so you can see it, clear up what I've got on here. If I wanted to integrate this on the calculator, I might want to come in here. Let me clear off the stuff I've got. And let's see if I'm in the right mode too. Let's see, what am I in? Mode. Let's see, I'm in, I need to be in radian mode when you start doing integration. But anyway, I'm in function mode, and that's what I really want it to be in. So y equals. And so I need to look at my function here, which is 1 divided by parentheses x squared minus 2x, x squared minus 2x plus 2, close parentheses. Now, we do a zoom, I'm going to do a zoom 4 window. That's a fairly blocked in window. And we see what kind of graph we get out of that. It's just a little hump in there. And we're wanting to integrate that from 0 to 2. And we can see on the graph here, that's most of this hump from right here on the axis over to here. So it's a good part of that hump. We wanted to find how big that hump is. And so how do we integrate doing a definite integral on here? Well, we're going to use our calc function. We're going to do second calc, and number 7 down there. Number 7 is the integration function. So I hit number 7, My lower limit is 0, so I put that in there, and then my upper limit in this case is 2. And I put that in there, and it tells me exactly what I integrated on the graph. See the graph? And then the value of that is 1.5707. And of course, we know that 1.5707 is exactly the same as pi over 2. So we got the same answer. And the decimal value there being 1.5707. And you can do pi over 2 all day long, and you'll always get that. So there you go. Calculator graph. And just to remind you, we did that. I'm going to put that on my paper here, that we had a graph that came out like this, didn't we? And we found the 2 was somewhere over here. And so we found that interval. This is from 0 to 2. And that area turned out to be pi over 2. Cool. Very good. A little interesting problem in itself, right? Okay, let's do one more here. One more of these completing the square problems. Here is the integral of 1 over the square root of minus x squared minus 4x dx. So again, it doesn't quite fit any of our formulas, but we're going to look at this minus x squared minus 4x that's here. And we're going to rewrite that as minus a parentheses, and we now have x squared plus 4x. And we want to complete the square on that so that it will be looking like a square binomial. And of course, in this case, it'll be x half of 4 is 2. It'll be x plus 2 quantity squared, provided I add 4 and subtract 4 on there. And now it's just this minus 4 left over in here. So this expression is exactly the same as the upper expression. And so we rewrite all of this. We multiply by the minus and rearrange it. It becomes 4 minus x plus 2 squared. And so that's where we come back over here, and this becomes dx over the square root of, and now that has been replaced with 4 minus x plus 2 squared. So again, a squared is 4, a is 2, u squared is x plus 2 squared, u is x plus 2, du dx. Fits the arc sine formula perfectly. So we rewrite this as arc sine of u, x plus 2 over a, which is 2. This is an indefinite integral, so we put plus c, and there's our answer. So we got that. Fun, fun, fun. Completing the square. We get to you completing the square a lot of different times. And so that's one of the things that that we will try to do from time to time. I think I'll let that be it for today. I think that seems to be like a good stopping point. We've done a lot of fairly complicated things. I don't know if you're going to have any more complicated than that or not. But at any rate, I hope you have learned a little bit out of this. I hope I haven't made too many mistakes, but I'm sure you'll tell me about it if I did. In the meantime, I apologize for having to miss class this morning. I hope making you have to look at a video like this won't be too insulting, and I hope it won't have to happen too often. But at any rate, good luck, have fun, and I will end it for now and see you in class on Thursday. Bye-bye.